on logarithm and exponential. This work is going to be the foundation for everything else you do. You know, you can see we still have lots to cover in the notes, but these are the absolute foundations. So to put the summary together, right? So we have all these, you know, exponential function, the examples of exponential function, okay? So don't forget this general form. The general form is this, right? The general form is b raised to the power x, right? Where b is greater than 0, not equals to 1. So under this big umbrella. And for logarithm, what is the general form? It's a log base b of x, where b is satisfy the same description. Okay, and these are the examples. And what is it going to be used the most? Right, the one you're going to use the most is E and ln. And they all have similar properties, okay? But depends on your future fields of study. So if you study biology, and you might be using certain functions with, you know, different bases, exponential functions, or you study social science, then you could be using other exponential functions. But if you study calculus, you're taking the next course, right? Then you're going to be using e to the power x and ln x a lot. Okay, so without further ado, graph-wise, okay, I prepared 2 quizzes for you on Monday for this week already, okay? And there certainly will be more. I think I might be giving you just one more quiz, okay? Other quiz about exponential, I will give you maybe later so that you can constantly review. So if you look at these curves, right? Well, last week we covered these relative positions, and you should be able to mark which one is which with certain given points. And these are the exponentials, the 4 exponentials together. And these are the 4 logarithms together. And this picture, of course, is both exponential and logarithm together. Okay, you can see that now we understand why they're called families. They're in the same family, right? They are in the same family indeed. Okay, do you guys have any questions on homework? Actually, I didn't assign you homework last week after a certain date, and today I will assign you homework. Okay, but you can see you have to study the lecture in order to do the quiz. Okay, so the intention is that you should study the lecture over and over again in order to be able to score perfectly on the quizzes. I want you to score perfectly on the quizzes. Okay, there's nothing that's on the quiz that if you watch the lecture, there will not be any surprise questions at this time and in the future. And we closely focus on these concepts and the application of these concepts. And we do this over and over again. So I see a hands up, Angelica. Go ahead.
Last night on the quiz, I believe that there was a mistake for number 8.
There's a mistake on number 8.
Yeah, the question was log base b of b, where 0 is less than b but cannot equal 1, but the answer was 1.
Hold on. Which quiz are you talking about?
It was I believe 6.
Quiz number 6. Well, thank you for bringing this up, but let's take a look.
Professor Roy.
Yes.
Yeah, so I had gotten that question wrong too, but then I just redid it and I put 1 again, and then it marked it as correct for some reason.
Okay, let's take a look. Okay, let's take a look. I'm glad you guys can identify a mistake. So let's see what kind of mistake that is. Right, this is which one you're talking about? Is
It's
this the
question 8.
Oh, there's no mistake here. This just is specifying what B satisfies. Your answer, you should put the answer for log base B of B. The answer 1 is correct, but I didn't make any mistake. So this is a typical mathematical language. You write an expression, and in this expression, there's a B. Okay, and this where just telling you B satisfies certain condition. Okay, so there's no mistake here. Which is how you read it. Okay, it's a question is how you read it. So the question is, you need to give the answer to log base B of B, but this phrase here is to tell you what kind of value for B. B is larger than 0 and not equals to 1. Does that make sense, Angelica? Did that confuse you?
Yeah.
Does it still confuse you now?
No, I understand now.
Okay, so this is not a mistake, but thank you for bringing this up, because sometimes as you read the mathematical language, when we read mathematical language, right, there are a lot of us actually not quite used to it. But what do we, in mathematics expressions, every symbol need to be specified. So this is a very good, this is a very important practice. And of course, as I was making up this question, I could just remove the where, but I just feel it would not be as rigorous if I removed it. So I left it there. Okay, so you often read this in some textbooks. They will use certain symbols and they will tell you, okay, T represent this, Y represent that, and so on and so forth. If you keep doing this in the future, when you start writing code, it will be an amazing habit. It will be amazing habit, because when you start writing program, every variable you use, I mean, for a lot of the programs, you have to specify what type they are. If you ever not specify a variable, your code is not going to run. Your code is not going to run. So that is very much from, is I would say, it's, you can say it's a computer science habit. It's actually a mathematical habit. All right. Okay, any other questions? Any other questions? All right, let's see. There are 2 chat messages here. Okay, good. Okay, got it. Very good. So let's go back here. Okay, so we have done exponential logarithm, and next today we're gonna have a change of gear. So we're gonna get to. Can you go over the last question for the next quiz? Can I go over the next question?
The quiz after this one, you know how there were 2 quizzes?
I know, but we have an issue here. I will be happy to go over with you. There are 2 students. They were asking for extension of this quiz for some personal reason.
Oh, okay, that's fine.
So, but if you want to ask me, maybe you want to ask me during my office time.
Okay.
All right. So sorry about that. Otherwise, I'll be happy to answer that question. All right. So don't forget it, okay? Do remind me of this question. So either come to my office or ask in class, okay? And today we're going to get to trigonometry. Do you think it's about time? And this table I put here certainly is not as complete because we did a much more. We actually did more than this, right? For example, we have those. We're giving you those points, right? We're giving you those calculus observation, right? We had those calculus observation here. So you can certainly put them over there, right? Do you guys still remember? Right? You look at the graph for exponential function, and you can say as, let me just put it here, as x approaching negative infinity, right? And the function, all of these functions, they approach what? They approach 0 from larger than 0. You know, these notations, when I taught calculus classes, and just to get these notations right, there are always a group of students that get it and the group of students don't get it. There are certain people in the calculus class, it takes them like half semester to get it. And along the way, they have missed points left and right. Okay, them lost points left and right if they could still stay in the class. Okay, I guess this is it's a habit that's hard to, it's hard to get used to. It's hard to get used to, okay? So that's why I decided, okay, I'm going to introduce it as early as I can. And I want you guys to see how natural these notations are, okay? So this is positive, this approaching infinity. And the other one, which is very, very important, right? As x approaching 0, right? These F inverse functions, all of these, they're going to approach negative infinity. And the other ones, of course, it's similar to that one. Okay, so I'm just going to copy and paste and change this to inverse. These are the two families of very important functions, and these two families are related. They're very much related, okay? And so all these concepts, right? One-to-one function, increasing function, decreasing function, they get to be used, okay? Another important property I wish to remind you of, which we have covered, okay, we have covered, is that for these two functions, right? They each have a correspondence. For example, if f is 2 to the power x, log base 2 will be its inverse, right? So these pairs of inverse functions to each other are very important, in particular for the E and ln. Okay, they all satisfy this relationship, right? F of f inverse of x equals to x for this, you can see that these axes, right, is an inverse function, which are the log functions. So the x must be from the domain of f inverse. So these will be true for x is larger than 0. Okay, and the next one will be f of inverse of f of x. And that's going to be equals to x. And this f are the exponential functions. The exponential function has a domain of all real numbers. Therefore, this x is going to be from the domain right here. Okay. So as a result of this, there's something interesting happened. Okay. I want you guys to look at the log 3. Log 3. Okay. Could you guys find log 3? I don't know which page, if someone could find it, because I'm using this old version of log 3. Some of these expressions in log 3 you're going to use in calculus. I can even tell you which chapter. I think will be chapter 3. Is that right, Farouz? Right?
Probably.
I'm sorry?
Yes.
Approximately, right? Approximately. So what you see here, okay, what you see here, you see these 3, right? So for example, the first one, log base 3. Maybe I should choose a log base 2 or something. I actually don't have a log base 2. Never mind. Just do log base 3. Okay. And this is a 5. Wow. What does that equal to? Doesn't this expression look a little weird to you? Some of you might have forgotten, right? Some of us might have forgotten. But what is it? Right? What is it? Right? What should it be? Well, this guy, okay, if we take f of x, so let me show you, I just want to give you another perspective. Okay, I'm sure you can do this with something you have learned before. I'm going to give you two perspectives. And the function perspective is very important. And it might have not been taught to you. Okay, it might have not taught to you. But having these skills of manipulating these algebraically is useful for you. Okay. All right. So without further ado, the first one perspective, right? One perspective is that we start with definition. We just forget about these things, right? We just forget about this function inverse. Let's just forget it, right? So from your past experience, you have learned the logarithm and stuff like that. So do you guys have your paper pencil with you? Look familiar. Yeah, so someone looks familiar, right? Good. All right. In the entire section about logarithm, the definition is the king. And what is the definition? The definition said log base b, right, of omega. You see, I have this single focus. Why do I practice these focuses? Because I want you to practice it too. Okay, in your calculus class, calculus 1, you will have focuses too. Your focus, number 1 is a limit. Number 2 is a continuity. Number 3 is differentiability. And number 4 is integration. They each have their focus. And where is the focus? Definition. You have to constantly look at the definition, apply it. Look at the definition, apply it. And look at the definition, apply it. If you keep doing this, you always get A. You have no choice. You keep getting points. If you don't, you keep losing points. Am I right, Farouz?
Yes, ma'am.
Focus. So I'm showing you how to keep the focus. How to keep the focus. Okay. All right. So focus is the definition. If you understand the definition and know its variation and know how you apply, right? And the end result is what? The end result, you don't have to memorize anything. You just be very familiar with this, a couple of definitions, a couple of theorems. You just keep using them. In the end, you don't have to memorize anything, nothing. You don't even need the flashcards. You follow me? Now you do, but soon enough, you won't need them. When you need them, they will just come to you. They will just come to you. You follow me? Then you have no moments to say, oh, I just go blank on my exam, on my test. There's no way you could go blank. You can't. Impossible if you keep doing what I show you to do. Okay, so get your paper, pencil, and derive with me. Okay, B. I always want to make sure you have these in your mind. A complete definition. A complete definition. Now, when this definition applies to base 3, when base is 3, right? What would it become? If this definition becomes 3, the base becomes 3, what has it become? This would be base 3, right? Base is 3. So this is no longer needed. Right? So this is the definition of logarithm base 3. From this definition, you can see this relationship. If I take this guy, you copy that sentence? If I take this guy, right? And the triangle, in the place of triangle, on the other side, it tells me triangle is log base 3 of omega. So left is right, right is left. I just do substitution. So I copy and paste and replace that. The consequence of this substitution, what do I get? What do I get? Look at this. Do you guys see that? Yes? Do you see that? So what should the answer be here? What is the answer there? Anybody?
5.
That's it. Did you see how that, if you did it, did you see how easy it was? Yeah? Everybody. Now, so that's the first perspective. The second perspective. Okay? The perspective. So this first one, the perspective of a definition. Okay? The second perspective is from the inverse function perspective. Because what do we know? We know this fact, right? The second perspective, the perspective of the inverse function properties. And what is it? The inverse function perspective is here. The inverse function perspective is here. Okay. In particular, if you look at the first one, okay, f of f inverse of x, what would that be? Because we know that two properties always true, right? If its function is 1-to-1 and its inverse is F inverse, that's always true. Okay, this is something that's always true for a function that inverse to each other and for this particular one. So this is always true for exponential logarithm function. So from that perspective, I will have F of F inverse would be this guy, right? And then what? What is F? F is 3 raised to the power of what? That, right? And this identity tells us it is always equals to the input. You see that? It always equals to the input. Now the input is 5, right? Now the input is 5. This is true for any input that's a fitting for the inverse function, which is in the domain of inverse function. So when this guy is a 5, what happened to this? So this is going to be what? This is 5. So this is the second perspective. You guys see that? This is the second perspective. You got it? So for exponential functions and logarithm function, we have this property. Then how about trig functions? That's what we're getting to. That's where we're getting to. For trig functions is going to be similar, but there will be some new. There will be some nuances there. There will be nuances here. So all of these I'm doing here is preparing you not only for your calculus classes, but also to have better understanding. Therefore, you don't have to memorize anything. Okay, so now let's look at E. Let's look at E, right? So we've done these properties for log base 3, right? So let's look at log 3. Let's pick another question. Let's pick another question. Okay, log 3. Log 3. Do you guys want to try one? I'm gonna let you try a few, okay, before we get to that stuff, and maybe we will do a breakout room. The two exercise I wish you guys to do would be number 2 and number 3. Number 2 and number 3. If you want to stay in the main room, you can. So these are the two, which is a 5 to the power of log base 5 of 6. The next one is 10 to the power of common log 3. Okay. So what I like you guys to do is that you have seen these two perspectives, right? You've seen these two perspectives. I want you guys to try your hands on deriving them yourself. Could I expect you to try to do that?
Professor, can I? Oh, yes. Number 3, 10 to the power of log 3.
I want you guys to try these different perspectives for different bases. 5, 10. Okay. And you're going to do it on your paper. I'm going to create a breakout rooms. Still, you self-choose, and Farouz is going to be in charge of one room. And I'll be staying in this classroom.
I copied the question on the board, Professor.
Yeah, so you work on number 2 and number 3, and you look at these two perspectives. Basically, you're applying definition. You're applying definition. So this guy is a definition. This is a general definition. From general definition to special case. The special case is b equals to 3. And the other one is a compositional function. That's the other perspective. Okay, ready, set, go. So I'm going to open all rooms. Right. Okay, if you stay in this room, are you trying it? I want you to try it. I wish you to try it. Two perspectives, okay? Two perspectives. One, so you're going to be working out for base 5. Okay, sorry about that. And for base 10. One is for base 5 and then one for base 10. So from the definition, you derive that. And the other perspective is function and its inverse. So you have a function of 5 to the power x, and the other one is log base 5x, and the other one is 10 to the power x and common log x. You practice with that. And you do the composition. You do the composition. Okay, you're making your composition. Right? For those of you who stay in this room, and if you want to, you want me to do something to check your work or anything, please don't hesitate.
Professor,
Yes,
can I send you a picture of my work through Pronto?
of course. Do that. All right. It's come. Hey. Phone. I was just looking for my cell phone. Did you send it to everyone? Or just to me?
No, just to you.
Okay. So I'll keep it that way. Yeah, I think you got the hang of it. But in general, once you know how to derive this, and typically your answer is just, I'll show you how to express your answer. Okay, and there's some. Yeah, so I'm checking the details of your work. Not a problem. Yeah, it's good. It's good. Isn't that pretty easy? Once you've done it, it's really easy, isn't it?
Yeah, yeah, I just got confused with like the 6. I just didn't know where to put it. But
You got it. You got it, right?
yeah.
Yeah. So you just have to put it. You just have to put in your own practice, isn't it? When you see it's just a substitution, or you just do the you know the composition of functions, and then it's very straightforward, isn't it? But that may not be for everyone. It's everybody. Just take your time just to. I just want you guys to kind of do like monkey see, monkey do, because that's what I used to do, and then you know over time you kind of get it, right? But you have to commit yourself to the steps by your own hands on the paper. That's the part that you must commit yourself. If it's in a classroom setting, I'll probably let you guys, you know, do it on the desk and I walk around, but now we cannot do that. We cannot do that. Okay, so for 5, right? So for 5, you pretty much do the same thing, right? For b equals to 5, what happens? You copy that, you look at your definition, right? And then this is a 5. And this is a 5, right? And this condition is no longer needed because b already satisfies it. And the next thing you do, you look at, oh, this is in this relationship. I'm just basically playing with it because the triangle is also this guy, and these two are the same. Therefore, you just replace the triangle by its equal, right? You just substitute among the same things, right? So when the exponential base and the logarithm base are the same, these two are both the same. And before logarithm, there's nothing there. It's just 1, right? So before the logarithm, it's really just 1 times that, right? So you can omit it. So whatever that omega is, of course, omega has to be in the domain. And so whatever that omega is, and it's going to be, you know, this whole thing is going to be that omega. And in this case, we had a 6, right? So if this is 6, and this is going to be 6. If this is 8, and what this is going to be? It's going to be 8. If this is x, and this is going to be x. You guys see that? Does everybody follow me?
Do you think that you could go over 10 log 3? I'm a little bit stuck.
Okay. So you got this part, right?
Yeah.
When for the 10, for b equals to 10, right? You will have you still have the same definition. Of course, the definition doesn't change, right? This definition has never changed in the past 100 of years, and it will not change in the next 10 million years, right? So this is 10, and that is 10. And this is going to be shorthand notation, and that's it. We don't need this part anymore. Do you guys see that? Right, you just take your time to do it, really. And in this case, right, in this case, you will have the triangle, but this time the triangle is log omega, common log omega. So you just replace triangle by its equal. Just replace triangle by its equal. And that's it. So this omega has to be from the domain of log, which is larger than 0, right? So whatever it is, okay, I'm going to close the rooms. So whatever this is, if this is 1,000, and this is going to be 1,000. If this is and of course you have to check these things, right? Base 10, log base 10, and there's nothing before log. So if this is 1,000, that's 1,000. If this is 0.5, and this is going to be 0.5. You can see that? If this is a square root of 2, right? And this is going to be square root of 2. Right? And if this is pi, and this is going to be pi. You guys see that? That's what it means. Okay. But if you look at the compositional function, okay, you guys must know how to do compositional function. Otherwise, you're going to have a hard time at a chain rule, chapter 3, calculus 1. Composition. Why do I want you to do the composition? Why do you think I want you to do it? Because I want you to get points there. Yeah? Now we're doing composition. Later, we're going to talk about decomposition. You have to know composition and decomposition in order to get those points in calculus classes. Okay, so now let's look at the function perspective. And I believe everybody is back, right?
Yes, Professor, we are here. We
Thank you,
definitely,
Farouz. Thank
you're
you,
welcome.
Farouz. Did you have
Professor,
enough time?
yes, and we definitely need to see all these two examples one more time if you show it to us, because build up confidence we need. We need
Okay,
build up confidence.
so for base 5 and base 10, do you guys see that? What did you do with them? Did you, I'm sorry, I didn't go in the room. Did you do this part? Did you do the composition or not yet?
We use the inverse function method to answer one of the question, and the second, actually we used both methods for the first question. Second
Okay.
question we needed probably to practice more, but maybe here you can just let us.
Yeah, I'm going to show you the second method. Right?
Thanks.
The second method. The second method, to be able to do the composition, you have to be good at doing the composition in order to do the decomposition. Okay, you need a lot of decomposition in Calc 1. Chain rule, chapter 3. Okay, chain rule, chapter 3. I've seen so many students in Math 190, when they do chain, when we taught the chain rule, when I taught the chain rule, some students got it, some students just lose points all over the places. And much less to say, after chain rule, you're going to have, the other sections will also need the same skill, Okay, so this is what they're preparing you for. So now let's look at for base 5. Right, let's look at for base 5. If this is a base 5, so this is base 5, what would that be? We know that this is true, right? We know this is true. Right? True means that no matter what positive number you put in there, there's going to be, so there has to be positive, okay? Has to be positive under the circumstances. Suppose this is 2 and this is going to be 2. If this is 6, this is going to be 6. But what is this? You can't just give your professor this thing when you're given the circumstances like that. right? You have to be able to apply this to the specific situation here. Do you guys follow me? So now let's apply it. We know that this is going to be equals to 6, right? This is going to be equals to 6. But what is f inverse of 6? What is f inverse of 6? So this is f inverse, right? This is f inverse. When this is 6, input is 6, and this is 6. So what f inverse of 6 is log base 5 of 6. Right? And now we're composing equals to 5 to the power of the input, Now the input is this guy. Okay, so 5 to the power of, okay, this is f5 to the power of x, right? To the power x. Now the input is replaced by this guy. Sorry. I'm going to copy this one more time. So you see the correspondence, right? You see the correspondence. When the input is replaced by log base 5 of 6, and this input is also replaced by the same input. You guys see that? So that's what you get. And what does this equal to? Someone told us it's 6. You guys follow me? Yeah?
Yes.
You got it? You want me to do another example?
Practice makes it perfect. Better,
Practice
fast.
makes perfect. I think by this time you guys are probably already perfect.
Yeah,
Okay.
can you show how to get the 10 log 3?
The 10, right?
Yeah, using the inverse way.
All right, let's do it. We just need to practice more, right? So when this is base 10, what happens? When this is 10 to the power x, and this base will be 10, right? If this is a base 10, we can shorthand this notation just as log. Okay? And then what? For this pair, the property still applies. This property still applies. This property still, so this is true. You guys follow me? It's true for any pairs of inverse functions. In particular, so we're just applying this result. Okay, so now f of x is 10 to the power x, and f inverse is log x. So what do we do here? This is going to be, so if this is true for any x is greater than 0, it is certainly true for 3, right? Because 3 is positive, isn't it? Do you guys hear that logic? If this is true for any x equals to x positive, any positive number, it certainly is true for x equals to 3, right? Yes? Because
Yes.
the first, I'm sorry, go for it. Go
I
ahead.
confirm it, yes, Professor.
Thank you. So the logic is, this sentence says, this is true for any positive number. Now I pick a number which is input equals to 3, it is certainly true, right? So then we just look at the details. If this is 3 and this will be 3, then what is this guy under the circumstances? Well, first you deal from inside out, right? So you're going to try to see what is F inverse of 3? Well, I know what F inverse of log X, right? So F inverse X is log X. So F, if input is replaced by X, this is going to be just log 3, right? Yes. Therefore, one step further, this guy will be replaced by its equal. And then F is applying, this rule of F is applying on log 3. But what is F? This is F. Okay, what did I do? Okay, so this is F, right? And F says input X is going to power 10. So now input log 3 is going to do what? Is going to power 10. So log 3 is going to power 10. Follow me? And that's going to be 10 raised to the power of log 3. And we already know this is true. Therefore, this guy has to be what? Has to be 3, right? You guys follow me? From general to special. So when you have a general case, you can always apply to these special cases. That's why math, when we do math, we try to be as general as possible. So in your calculus class, you're going to learn a lot of general theorems and stuff like that. And so you can apply them to polynomial, exponential, sine. You can apply to those functions. And one theorem will tell you, all exponential functions are continuous. It means all. And then you can apply to special cases. Does that make sense? Okay, it's like, the law of land in the United States of America applies to everyone on the land, which implies what? It applies to Angelica. It applies to Farouz. It applies to Noah. It applies to Christopher. And of course, it applies to me too, right? The general statement is that the law, there's so many laws, but it applies to everyone. So you have a general statement and you have each individual cases, but that law apply to each individual case. Does that make sense? Right? So I want you guys to make sure that these things go through your hand. Don't just watch. You have to write it down. Write it down. I don't know about you. Any math I do, if it doesn't go through my fingers, it's gonna be gone. If anything math doesn't go through my fingers, it's going to be gone. I think this is not just me, isn't it?
I remember. Yeah, I remember.
That's most of us, right? That's most of us, right?
Professor, I remember we have 3 types of learners, categorized to 3 types: audio learner, video learner, and kinesthetic learners. So kinesthetic learner are the ones using their hand with the paper and pencil, writing down.
But when you learn math, you have to use your audio, you have to use your visual, you have to use your hands, whatever. Right. No matter what type of learner you are, when it comes to learn math, you have to use every senses you have, including vision, hearing, reading, writing. You have to use everything that you have.
Very true.
Okay, you can't say, oh, I'm going to learn by watching. No, you're not going to learn it. Sorry. Even though you're a visual learner, you're not going to learn math that way. if you can learn math and ace all your exam, I don't want you to be in my class. Please, you are a genius already. And I don't like to teach genius. I can't teach genius because I'm so dumb. I can't teach genius. Do we have a genius in this class? Okay, or some people say, I can hear I learn it, not with math. Maybe with music, not with math. All right, guys. We will be addressing to those, aspects that you have. For example, we do the graph, right? But after you have that vision, you still have to write it down. Okay. All right, so so these are the two different perspectives. Did you get it? Okay. And we will see that these two properties, right, that apply to exponential logarithm, right? That's apply to an exponential logarithm. So here I'm gonna just make sure, because we already have it down below, but just to make it more complete, right? B to the power X and F inverse is equals to log base B of X, where B is larger than 0, not equals to 1. So we have, I think we're pretty much done with addressing these two issues. Okay, but next, when we come back, okay, I wish to give you guys a break. Could you come back at 12:10? I'm giving you 6 minutes break. And we're going to be addressing those expressions in log 3 with base E. With base E is the thing you're going to use in calculus for sure.
Professor, you meant 12:20. Right now it's 12:12.
12:20?
Yeah, right now it's 12:12 or 12:13. So we come back 12:20.
12:20. I'm sorry, 12:20, please.
Thank you.
Okay. Sorry. So please come back at 12:20 p.m. Okay. So you kind of have 5 minutes break. Sorry. Maybe I can let you go earlier. 5 minutes earlier. Remind me. Okay. I'll see you in a few minutes. Please come back.
I'm here.
Come back. Come back. All right. So all of these forms, you can see, I just want you guys to practice so you get familiar with it, right? So it comes somewhat more natural to you, right? So let's look at the base E case. The base E case. What is that base E case, right? That base E case, for example, we have let's look at number 5. Okay, actually, I'm gonna bring this to So we know the answer, right? So this is 6, right? That's a 6. You already got it, right? This is 3, right? So how about number 5? Okay, number 5, we have an E raised to the power of ln 5. What is this? What is it? Right? So this will be the situation that we have f of x instead of, instead of being base 5 or base whatever, right? It will be in the situation of base E. okay, base E. So this is going to be E, and that's going to be natural log X. You guys see that? Now, two perspectives I want to give you, okay? You should master at least one of them. Master at least one of them. From the definition of function of logarithm, right? What's the definition of logarithm? I'm just going to copy and paste, right? Along the way, so you guys get to watch this thing we just did. The perspective of definition. Definition. Okay. If the base is E is larger than 0, not equals 1, so I can remove this guy. Right? And this becomes E. Right? And with that, E raised to the power triangle equals to omega. Right, so they're locked in this relationship. They're locked in this relationship, right? They're locked in this relationship. And the triangle, of course, we have a shorter hand notation for it. It's ln omega. So this triangle is the same as ln omega. So it's a pure substitution. It's really just substitution. Do you guys see that? It's just a substitution, isn't it? Okay. So when you observe this identity, right, omega must be from the domain of ln x, right? Meaning omega has to be positive. E raised to the power of ln. So natural logarithm base is also E. And in front of ln, there's just number 1, right? It's just number 1. Oops. Right? There's nothing in front of it. That means 1 times it. Mind 1 times it. If you have a 2 times it, that's not going to work. Okay. Now, 1 times it. If you have these match, right? E is the base of exponential. Ln is the base of E. Therefore, whatever this guy is, whatever that omega is, if this is 5, this is going to be 5. If this is 0.0001, and this is going to be what? 0.0001. You follow me? And in this case, we have a 5. As long as it's in the domain of natural log function. Do you follow me? All right, so let's look at the other perspective. Okay, inverse function properties. Inverse function properties. What do we get from inverse function properties? Right? We will compose, right? And then we have that property. What does that property say? Right here, right? That's what the properties say. This is true. Oops. Okay, this property is true. Okay, and what does it say? Your input to the inverse function, it produces an output. That output is served as input for the f function, and that produces an output. That output is going to be exactly the same as your input. So, right, we used to draw the chart, the chart, the flow. Do you guys still want to see the flow? You kind of already get it, right? You already get it. Otherwise, I would love to draw the flow for you. You guys want to see the flow? Are you guys tired?
No, let's see the flow.
Let's do the flow. Oh, right. Let's do the flow. Okay. The flow. Okay. The flow actually borrowed from flow chart in computer programming. Okay. So my input X, okay, because X will be immediately acted on by F inverse. So this X has to be in the domain of F inverse. Do you guys follow me? So symbol doesn't matter. It depends on which symbol it, what the function that's work on it, which rule applies to it. So you can use any symbol you want. You can use apple, orange, whatever you want. But the rule applies to it determines what it can be. You follow me? All right. So of course, this X belongs to the domain of ln X, because ln X domain is, the input must be positive. So you choose that input, and that input is, how we have the, it produces an output, right? And this output is served as an input again for F. It produces output. So the F of what? The input is F of inverse of X. And this property tells us, right? As long as your X is positive, this is always going to be X. That's what it's saying. Doesn't matter what X is, as long as it's positive. Okay. So when we see this, so let's see if the input is 5, right? 5 is a positive, right? 5 is a positive. So what happened to F inverse? So we apply the F inverse function, right? And what do we get? We're going to get ln 5, right? Just plug in, right? 5, 5. And ln 5 will serve as the input for F. And F is a different rule. F is a different rule, right? And F rule is e to the power X. That's the rule for F, right? So this will be the input, and input will replace X. So in the end, we get e to the power of ln 5. And we're told that that's going to be the same as X. And what was X? X was 5. That's the flow. And mathematically, we don't use this. Okay, you don't see a lot of these flows in any textbook. I'm using it a lot recently, right? But what you do mathematically is really just we kind of make it shorter, right? So if this is 5, we're going to write it as F of F inverse of 5. That's just plug in. So I'm going to get ln 5. And F of ln 5 is going to be e to the power of ln 5. And that's going to be equals to 5. So you can see from flow to the actual mathematical expression, the mathematical expression certainly has to cut down those arrows, those other accessories. So mathematical notation is much shorter. Every notation implies a lot of things. You really have to understand it. Otherwise, you won't be able to sustain yourself very long. So it's absolutely necessary you have to write it down, no matter what type of learner you are. Don't tell me you're a visual learner, you only watch. Don't tell me you're an audio learner, you only listen. You have to listen, watch, and write it down. And think. And think about it. Okay. So do you guys want to try some more E, right? So I'm going to give you some assignment, okay? Number 6, 7, 8.
Sounds good. Sounds good idea, Professor.
Yeah, let's practice. Let's practice. Practice makes perfect, right? So now log 3. I want you guys to do, maybe you want to do number 5 one more time, right? Number 6, number 7, number 8, number 9, number 11, number 12. How about that? You can stay with me, or you can go with Varus.
I don't have a question, Professor.
You have a question?
No, I do not have those questions with me. Is that something we can write it on the board?
Oh, of course. Yes. I'm going to write down the questions here.
Thanks.
So number 5 is the one we just did, e to the power of ln. Okay. Number 6, e raised. Farouz, you don't have the note?
I didn't open it. Kind of
Okay,
having.
but you have access,
I should. Yeah, I should definitely.
because otherwise I can send it to you. And number 6, number 7, e raised to the power of ln root 3 8 means e raised to the power of ln 1 over pi. Number 9, e raised to the power of ln 1. Number 11, okay, e raised to the power of ln pi. $12, e raised to the power of ln square root of 5. Okay, the room is open.
Thank you,
If
Professor.
you want to practice with Varuz, or you want to stay with me. If you stay with me, I'm going to just hold on a little bit to let you guys to try them first, and then you bring the question to me, okay? Please do that. There's 7 breakout rooms. Okay, we have 17 people in the breakout rooms. All right. So feel free to ask me questions. So derive a couple of times if you feel like, I'm not sure, just derive a couple of times from the definitions perspective. Okay, from the perspective of definition, and soon enough, you're gonna be a master of this all. I'm certain about that. That's all you need. Just practice. Are we good? All right, let's see. Yeah, I think you got it. All right, you got it, right? Once you know the mechanism, your teacher in calculus class, all he or she expected of you is just write down the answer. So what is the answer? What's the answer for this guy? It's just 5, right? What's the answer for this? Y. What's the answer for this guy? What is it? Root 3, right? Radical 3. Sorry. Right? How about this one? Whatever that omega is, that's your answer. And this one is just going to be 1, right? How about this guy?
Pi.
Pi. How about this? Right? You got it? That's all you need to know. And this form will be much more exploited in calculus class. It is really just a symbol. Okay, you can put omega there, you can put, you can put omega there. That's what we did. Right? Then you say, hey, I don't like omega. I want to be using y. Then use y. Then you say, hey, I don't like y. I want to use heart. Do it. No problem. As long as they're from the domain of the perspective function, you're good. So after all, it's just a symbol, isn't it? So this is the form you're going to use exactly. Okay, with y substituting the heart. All right. So that's log 3 is your homework. Please do it, please really do it. Okay, so please really do it. And next, I think we still have some time. We still have around a little bit less than 20 minutes. If you guys don't have any questions about exponential logarithm, And I want to get started on trigonometry. Are you ready? Are you tired? You know, today's class ends at 1:20. Do you know that? Do you want to take a break? I give you 5 minutes break. Maybe I give you another 5 minutes to reflect on the logarithm, because next we're going to get to trigonometry. How about I give you five more minutes and you'll come back at 12:50. How about that? We're going to do 30 minutes of trig. All right. So come back